In this video, I'm going to talk about the time derivative of the expectation value of momentum. This video is part of a playlist on quantum mechanics. You can find the link to this playlist in the description below. Let's get started with the derivation. Now, this derivation is going to begin with the time derivative of the expectation value of momentum, and it's actually going to show that that is equivalent to something that is very familiar in Newtonian mechanics. I'll leave that as a little kind of surprise at the end of this video. It's linked to a theorem called Ehrenfest's theorem, which kind of brings together quantum mechanics and classical mechanics. It shows that quantum mechanics actually predicts a lot of Newtonian mechanics, and all those relationships in Newtonian mechanics can be derived from quantum mechanics. And that is an excellent idea. So let's go ahead and start with this derivation. First of all, what we need is the time derivative of the expectation value of momentum. So this is d dt of the expectation value of momentum. And if you remember from some of the previous videos, we defined the expectation value of momentum as an integral sandwich. So let's go ahead and write d dt of this integral sandwich. So we're going to have an integral from minus infinity to plus infinity of capital psi star times what's going to be in the middle of the sandwich? Well, it's going to be the momentum operator. The momentum operator is going to fit inside this sandwich. That's going to have h bar on I, and it's going to have a partial derivative with respect to x. And then we're going to have psi over here, and then dx. So this is our integral sandwich. This over here is the momentum operator, and we have a time derivative because we're taking the time derivative of the expectation value of the momentum. So let's go ahead and actually rearrange this and move the time derivative inside. We've done similar things, analogous things to what we're about to do in previous videos. So make sure you watch some of the previous videos in this playlist so you can get a sense of where this is coming from. So let's go ahead and move this derivative inside. And let's also take this little h bar on I and move that onto the outside. So if we move that h bar on I outside, we can actually turn it into minus I h bar. So let's go ahead and do that. So let's turn that into minus I h bar. And when we bring the derivative with respect to time inside, it's going to turn into a partial time derivative. And we're going to have the partial time derivative of psi star, and then we're going to have the partial derivative with respect to position of psi. And this is all getting integrated with respect to x. So let's have a look at what we have. This psi star has actually moved over here, right? So we've brought this time derivative on the inside. We've taken this constant out. Remember, dividing by I is the same as multiplying by minus I. And we've also applied this partial derivative with respect to position onto psi. So now we're differentiating psi, and this is all being differentiated by the partial time derivative. And why is it a partial derivative? It's because the integrand depends on x and t, but the integral just depends on t. So this is a total derivative, and when we bring it inside, it turns into a partial derivative. There's a video explaining that in a bit more detail earlier in this playlist. So now what we have is this messy expression on the inside. So I'm really interested in what this is equivalent to. So what we're going to do now is we're going to just focus on what's inside the integral. We're going to focus on the integrand. And we're going to do some manipulations, and we're going to get that into a form that is more familiar to us. Then what I'm going to do is I'm going to substitute back something that's equivalent to this into the integral, and we're going to draw a final conclusion for this video. So let's go ahead and do the rest of this derivation. So for the next few lines, I'm just going to focus on the integrand. So I'm just focusing on what's inside this integral. And we'll ignore the integral and this factor of minus I h bar out the front over here. So let's go ahead and rewrite this using the product rule for differentiation. First of all, let's differentiate psi star. So if we differentiate psi star with respect to time, that's going to give us d psi star dt. And when we differentiate this guy, we don't have to differentiate this guy. So that's going to give us d psi and with respect to x. So this term is just differentiating with respect to time of this psi star. Now what we need to do is we need to differentiate the other term. We need to differentiate this guy with respect to time. But here's an important observation. You can actually swap the order of derivatives. So if we differentiate this with respect to time and position, it doesn't matter if we differentiate with respect to position first and then time, or the other way around. So I'm going to go ahead and move this position derivative out the front, and I'll move the time derivative inside. So what that's going to look like is we're going to have the psi star, which is not differentiated at all, because we differentiated it in this term. And then we're going to have d dx of d psi dt. So can you see what I did there? I just swapped the order of the derivatives with respect to x and t. So this, we can also swap back. We can turn this into the time derivative of what we have over here. So this over here is equivalent to the integrand. I've just expanded it with the product rule for differentiation. So that's what this time derivative has done. Now, what we can do is we can use the Schrödinger equation and we can substitute it in here. So this is what we've done in some previous videos too. We're going to take this part over here, this partial time derivative of psi star, and we're also going to take this guy over here, and we're going to substitute in a modified version of Schrödinger's equation. So remember, Schrödinger's equation in one dimension has got this on the left-hand side. It's got IH bar times this. So we have to divide the right-hand side by IH bar. And what is that going to give us? That's going to give us this over here. So I'll put it in brackets. We're going to have minus IH bar over 2m. Then we're going to have the second partial derivative with respect to position of psi star. And then what we're going to have is a plus I over h bar times v times psi star. Now I'm going to try and squeeze all of this in here. This guy is still here, so this is just this little term, the partial derivative of the conjugate. So I've actually complex conjugated the Schrödinger equation, and I've also divided by IH bar. Now we're going to multiply this by this partial derivative with respect to position of psi, and then let's add to this term over here. So I'll try and squeeze this in. We're going to have psi star, we're going to have d dx of all of this stuff over here. So there's not going to be a minus sign. It's not a complex conjugate. It's just going to be IH bar over 2m. Then we're going to have the second order derivative of psi. And we're also going to have that potential term. That potential term is going to have a minus sign. It's going to be minus I on h bar times this potential term, which is going to be v times psi. Now, let's go ahead. I'll summarize what I did to go from here to here. So all of this is equivalent to the integrand. This integrand we expanded using the product rule for differentiation. That's how we got this. Then we identified these two partial derivatives with respect to time. And we used the Schrödinger equation and we substituted an equivalent expression. This expression has a complex conjugate. You can see there's a complex conjugate here and a complex conjugate over here. This expression does not have the complex conjugate, right? We have psi star times this spatial derivative of this, d psi dt. And we've substituted the psi dt as all of this stuff over here. So I want you to see that this guy is equivalent to all of this guy is equivalent to this, and this guy is equivalent to all of this. So the important thing is there's a minus I over here, there's a plus I over here, there's a plus I over here, and there's a minus I over here. And there's no complex conjugates on these psi's, but there are complex conjugate on these psi's. Why? It's because this expression over here is the complex conjugate of this expression. So those two expressions in the square brackets have come from the one-dimensional Schrödinger equation. Now we can move on and we can go to the next step. So the next step is going to involve grouping together some terms. First of all, I'm going to group together all the terms that have IH bar over 2m. So IH bar over 2m, I'm going to group together all the terms that have that factor. First of all, which term do I want to put up first? I'm going to take this term over here. You can see there's an IH bar over 2m, and it's multiplying this second derivative. So when I apply this first derivative, I move it inside here, that's going to give me a triple derivative, right? We're going to have to differentiate psi 3 times. It's a triple derivative. And I'm also going to have a psi star multiplying it. So I'm going to have psi star times a triple derivative of psi. So I'll go ahead and write that. That's going to be my first term that has I h bar over 2m as a factor multiplying it. So I'll have psi star and the triple derivative of psi with respect to position. So that's a triple derivative there. And we got that from this term over here. And we can identify another term. There's going to be another term that has I h bar over 2m. And that's going to be this term over here. And this term is going to multiply d psi dx. So this guy and this guy are going to multiply together when we expand this out. So that's going to give us a, it's actually going to give us a minus sign, right? Because there's a minus I out the front here. So we're going to have minus the second derivative of psi star. And then what we're just going to have is the first derivative of psi. So it's just going to be the first derivative. And that's what we're going to have over here. That's all the terms that have this factor of I h bar over 2m. So this term has come from this guy. We've got this guy with a minus sign, and we're multiplying it by this guy over here. So that takes care of this term and this term over here. Now let's take care of all the terms with I over h bar. So we'll group together all the guys that have I over h bar. So everybody that has I over h bar, I'm going to put them in this little square bracket. So what has I over h bar? Well, we have this term over here. That's going to have a v, psi star, and a derivative with respect to x of psi. So I'll go ahead and write that over here. We're going to have v psi star, and then we're going to have this guy, partial derivative of psi dx. And that's it for this part. So that's taken care of everything on this left side over here. We've also taken care of this one, and all that we have left is this guy over here. This guy is all that remains. So let's go ahead and write that guy out. So that guy, when we move this partial derivative of x inside, is going to have a minus sign, right? Because there's a minus sign out the front here. We're going to have minus, there's a psi star multiplying. So we'll have psi star. Well, we're also going to have this derivative with respect to x, and we're going to have to differentiate the product v psi. So we're going to have to use the product rule for differentiation again. Now let's just make sure we've collected all of the terms, right? We've taken this expression and we've regrouped everything. So all the terms that have I h bar over 2m, first of all, we got this guy from this term over here. We have psi star, and then when we apply this derivative, we get a triple derivative of psi. Then from this term over here, we have a minus sign over here. We have minus, we have a second derivative of psi star, and then we have a single derivative of psi. This combination is going to end up disappearing. It's going to end up canceling out when we put it back into the integral. So this is not very important. But this one over here is very important. That's where all the magic's going to happen. So how did we get all of these guys? Well, we got them from the I over h bar terms. So the terms that contain this factor. So we have a v, we have a psi star, and we have a d psi dx. So we have a partial derivative with respect to x of psi. And that's what we got from this guy. And then we got this minus term over here. And that actually gave us a psi star, a partial derivative with respect to x, and then we had this product over here. So that is what happens when you move this stuff and you apply it over here. Now what I'm going to do is I'm going to show you an alternative way to express this right-hand side over here. So this bit over here with the minus sign, we're going to rewrite that slightly. We're going to use the product rule for differentiation, and what we're actually going to find is that you can write this as minus psi star, and what we can do is, again, using product rule differentiation, let's first differentiate the v. So we'll differentiate the v. We're going to have dv dx. And then we're going to have a psi. Now this is the magic expression. We're going to use that very shortly. But first we have to get rid of everything. We have to cancel all the other stuff out. So this over here, psi star dv dx, that is psi, that happens when we differentiate the v. But we also have to have another term, and we have to differentiate the psi. So let's go ahead and get that term. That's going to be psi star. Then we're going to have a v. And then we're going to have d psi dx, right? We're taking a derivative of psi. Now, does this look familiar? Have a look at this expression over here. It's just a slightly different order, but you can actually swap the order of these guys and show that these guys are actually equivalent. Here we have a psi star and a v. Here we have a psi star and a v. And we also have a partial derivative with respect to x of psi. So this guy over here is actually going to cancel this guy over here, right? Because this is a minus and this is a plus. So all we're going to be left with is this times I over h bar. Now, I want to show you why this is going to cancel out as well. Remember that all of this stuff is equivalent to the integrand. So we're going to end up putting this back into the integral. But if you take a look at this, you can actually use integration by parts, and you can move some of the derivatives. You can apply integration by parts twice to this little combination here, and that's going to give you the same combination on both of these terms. So they're going to subtract, and they're going to end up giving 0. So this is going to turn into 0. And this is going to disappear. So all we're going to be left with is this times this inside the integral. And I'll write that out in a second. So let's write out the final expression, and then I'll make some clarifications on this little part about integration by parts. So the time derivative of the expectation value of p, or the expectation value of the momentum, is actually equal to, it's equal to all this. We're going to have a minus I h bar. Then we're going to have a factor of I h bar, which I'll factor out the front. That's coming from this thing on the front. And then we'll put all of this stuff inside the integral. And that's going to give us this integral sandwich from minus infinity to plus infinity. We're going to have this over here. We're going to have psi star. And here's what I'm going to do. I'm going to take this minus sign, and I'm going to put that minus sign in here. And I'll make this into an integral sandwich of the partial derivative of v with respect to x. And there's going to be a minus sign in here. I've moved this minus sign in the middle. And I'm going to complete this integral sandwich. Now, this is the integral sandwich definition that we used up here, right? But instead we had the momentum operator. Now what we're going to have is this over here. And this is actually, well, the h's are going to cancel. So this h bar and h bar is going to cancel. I times I, that's I squared, which is minus 1. Minus 1 times this minus sign is a plus 1. So all of these constants out here just give 1 out the front. They cancel each other out. And that just leaves us with the expectation value of minus dv dx. Now, that is the takeaway message of this video. I'll summarize that right at the bottom over here. So we're going to have the time derivative of the expectation value of the momentum is equal to the expectation value of the spatial derivative of the potential. Now, this we can identify is force, right? This is actually analogous to Newton's second law in classical mechanics. So we've actually used expectation values and all of these wave functions in quantum mechanics to reproduce Newtonian mechanics. So this is part of Ehrenfest's theorem. And it's a very, very important theorem in quantum mechanics. And we're going to go into detail and we're going to explain a lot about this theorem in later videos in this playlist. But the takeaway message from this video is this expression over here. So the time derivative of the expectation value of the momentum is related to this expectation value, which is related to force, right? Force is the time derivative of momentum in Newtonian mechanics. So there are a few caveats, there are a few little subtle nuances on what potentials are allowed here. There's potentials, there's restrictions on the types of functions that can be this potential, and you can go into those details, but we won't go into those details in this video. As a final little message for this video, I just want to cover the nuances in how we could set this equal to 0. Now, why were we allowed to set this equal to 0? Again, we used integration by parts twice. There's other ways to do this as well. You can do this with other little integral tricks. But the way that I'm going to show you is integration by parts. So when you do integration by parts, you can actually swap the derivative and move it onto another function in the product. And when you do that, you have to introduce a minus sign. And if you do that twice, you swap over a derivative twice, right? Because we have more than one derivative over here. You're going to introduce a minus sign twice. A minus times a minus is going to give us a plus. So that is actually going to give us the same sign that we started with. And these guys have opposing signs. So if we do integration by parts twice on either one of them, we're going to go back to the same sign. And we're actually going to get the same function. This is going to equal that. Now, why do we ignore the boundary terms? Well, it's because the boundary terms can be ignored because psi and psi star are going to end up going to 0 as x goes to plus or minus infinity, right? And plus or minus infinity, those are the bounds of the integral. So the bounds of integration are plus or minus infinity. And we know because of the normalization condition, psi and psi star are going to disappear as you go away from the origin to the very, very distant area of minus infinity and plus infinity. So that is why we can ignore those boundary terms. And that is why we can use integration by parts, apply it twice to this over here, and that is why we can make this into 0. So all of this business over here, everything in between here and here, this fits inside of the integral. So all of this stuff is actually equivalent to this. So that's the important takeaway message. We can actually use all of this quantum business to get Newtonian mechanics. Now, try and do this derivation by yourself and see if you can maybe do some different steps. Try and do some different tricks with integration by parts. Or try some other tricks with integrals and see if you can get this term to disappear and try and cancel out all these other terms so you can just get this expectation value at the end. You can watch all the other videos in this quantum mechanics playlist by clicking over here.